Okay, so welcome everyone to ME3571, Mechatronic Systems Modeling Lab number 2. So today we have a DC motor modeling task, right? So I think most of you all have sort of worked with DC motors up to some extent, right? So you all have done the MDP 2 module, MDP 1 and MDP 2 modules, and I think you all have worked with two forms of DC motors, which are stepper motors, and I think you all use brushed DC motors for the second lab. I'm not sure. Or was it steppers once again? I think you all used DC, right? Like normal DC. Anyway, so I think you all have experience, and I think if you all have started, I think some of you all have started working on the RC plane or design for mechatronics, and in the there, of course, you work with brushless DC motors, right? Where you have the permanent magnet stator to a permanent magnet rotor, right? So I think you all have sort of experience with this. So I will anyway. We'll recap whatever the knowledge you all have about this, and I will actually cover the basics like the operating principles and all. So you all know that there are like certain categories when it comes to motors. So if you take any mechatronic system, right? So actuators play a very huge role, right? Actuators are one of the most important aspects that we consider under mechatronics, right? So simply any mechatronic system has we can simply characterize those as the power element, the sensory element, the actuators, and then the control element, right? So when you talk about the actuators, there's a multiple type of actuators that we use. There's hydraulic actuators, pneumatic actuators. Then we have the pure mechanical actuators, which are also like hydraulic, pneumatic, are sort of like that. But if you take pure mechanical actuators, it's more of like where you have rigid bodies, right? And then we have these electrical and electronic actuators. So under these actuators, we have AC components and DC components. And I think you all comprehensively learn about AC motors under electromechanical energy conversion and electromagnetics in the second year, I guess, where you learn about induction motors and AC three-phase motors and all, right? So now our focus is on DC motors, and I think you all have some understanding about DC motors once again in that particular module, and as well as under systems engineering, right? So there actually you learn about the plug and play aspects of a motor, where how to like control a motor, how to plug in a motor, how to change the direction of the motor, how to change the RPM of the motor, what sort of factors to consider when purchasing a motor, right? So the current draw of the motor and all these like a much more practical aspect of motors, right? But under this module, we'll be more focusing, more of our attention will be given to the modeling aspect, right? So you all know a DC motor is actually like a mechatronic, like a pure, it's like a very good example for a mechatronic system, right? It has a mechanical component as well as an electrical component. So I will we'll go through how we model this, and you'll understand how these components actually come together, right? So you can go through the classifications, and I'm not going to like directly just go with the lab sheet. So I will explain. So you can later on go with the explanation and then refer the lab sheet, right? I'm not entirely going to rely on the lab sheet, but everything in the lab sheet will be covered, right? So okay, so we'll first talk about the basic operational principle of a DC motor, right? So if you talk about like the governing principle, right, which actually defines the operation of a DC motor, it's the Fleming's left-hand rule, okay? So what does Fleming say? So what he says is like, if you arrange your thumb, forefinger, and the middle finger perpendicular to each other, right? Then these particular fingers point in the direction of, so thumb points in the direction of the force acting a bit, and based on the magnetic field, right? So here we actually involved in the magnetic field, force exerted by a magnetic field on a current conducting element, right? So if we take, so I will draw that so it's much more easy to understand. If you like keep your, if you keep your like thumb like this, right? Thumb, your forefinger and your middle finger, okay? If you like, point them in this direction, okay? So if these directions, so these are perpendicular to each other. So if you like point your forefinger in the direction of a magnetic field, right? So we'll another color. So this is the magnetic field. We use B to identify the magnetic field, and say we have the current direction, this direction, and we have say the force exerted on this particular conductor will be on this direction, right? So this is like the theory that we use. So to understand this theory, what we'll do is we'll actually use a magnetic field. Okay, we'll have a magnetic field like this. So these are basics that you all have already done, I think, for A-levels, and then I'm not sure where you have found, covered this before, but I'll just once again go through this. So it's like this now. So we have the North Pole and the South Pole, right? And here we'll assume anyway, the magnetic field is going to be in this direction, right? Okay. So what we'll do is we'll keep a conductor inside. Okay, we'll keep a conductor inside this field. We'll keep a conductor in this field, and we'll give a supply. Okay, we'll give a supply of positive this direction, and we'll assume, right, this is like a much more like a sort of representative way, but we'll assume that everything's like this. Okay. Then in this case, we know the current is going to flow from positive to negative, right? So we know the field of, we know the direction of the magnetic field, and we know the direction of current. So if we apply the Fleming's left-hand rule, so we point our middle finger in this direction and our the forefinger in this direction, and we find that the thumb is pointed upwards, right? So there's a force acting on this direction, right? And this force, we can say, is equal to B I L. It's actually proportional. So for the force is proportional to B I and L, right? So we can, from here, we can derive that the proportionality constant is this, and we can derive this equation, right? So to increase the force, we can increase any of them, right? So how can we like actually use this in a like, you know, to our advantage? So we can, instead of one of these links, what we can do is we can have something like this, right? We can have something of this sort, conductor of this sort inside this. Okay. Now what will happen? So we will give the positive current from here, and we'll give the negative current from here, right? So there are say two terminals in here, right? Two terminals here, and we are giving power. Okay. Now what will happen? Now the current will go from this direction from here. So once again, if you apply Fleming's rule, in which direction, in what direction the force will act? It will act like this, right? Okay. So now the current will go like this, and then it will cross here. But here there's not going to be an issue because it's like parallel to the direction of the magnetic field. But once again, when it comes to this side, we can see that the direction of the current flow has changed. So the magnetic force, the direction of the magnetic field is constant, but the direction of the current is changed. So the force acting on this conductor should be in the opposite direction, right? Like this. So you can see now here there's a force couple acting on this, right? So when there's a force couple, what will happen? There's not going to be any translation, but there's going to be a moment around this axis, right? So so now there's a rotation. But what will happen if we rotate this? If we rotate this with this particular alignment, and if this is connected to this, then as soon as this rotates, the polarity in these two poles will be shifted, right? Let's assume that these are connected to each other. These are like, soldered. The terminals are soldered, right? Then of course, once you flip this around, then the direction of current is going to rotate. The polarity in the terminals is going to shift, and that will actually cause like oscillation. So one part will happen is this will keep on moving like this, right? Like it will have like oscillatory motion, right? So we don't want that to happen. We want a rotation to happen, right? So what we can do is we can remove the connection here, right? We can remove the connection here. So, and we can have some sort of like a, brush sort of a fixation, right? So whenever this rotates, this is actually separated from here, sort of like this. This part rotates, and each time it rotates, it will come and whatever in the other side will come and fit here, right? So the bottom line is that the polarity, the voltage in this point, this particular point will always be positive, and in this particular point, it will always be negative, right? So it will always be the polarity in the terminals will always be positive. Constant. Hence, the current direction will be constant. And since the current direction is constant in this particular order, the magnetic field is constant, and there will be a continuous rotation, right? So this is simply how we get a DC motor to work, right? So these are the brushes. These what we call are the brushes. So that's why we call the brushed DC motors, right? So these we call the brushed DC motors. We have brushless DC motors where we have the rotor as the permanent magnet. So we'll be discussing. I think I have discussed this under Mechatronics systems, but our focus is on a brushed DC motor, right? So this is the basic operating principle of the brushed DC motor. Any questions up to this point? I think this is something that you all are already familiar with. So, so this is like the operation of the brushed DC motor, right? So we'll now go to the modeling part. Our concern is with the modeling part. Okay, I will go back to the lab sheet. Okay, so this is this is like how actually it looks like. Okay, this is actually how it looks like in when you like look at the overall design. In the real case. So you have the we call this the armature, or the rotor we call the armature. So that's like it's simply like a coil, right? Like a coil of copper. What we call as the rotor, and we have the stator is actually like the permanent magnet, right? Here's the North Pole and the South Pole, and we have these brushes like this, right? In the terminals will be given power, okay? And we have just two terminals where I actually power up the brushes. It will go, the current will go through, and the magnetic field will do the other work, okay? So so this is like now we are trying to model this, right? So we actually don't have to think about the stator here, right? So stator in here is like it's like a permanent magnet. And you know that when you're like modeling magnetic devices, we model it as an inductor, right? Why is that? It's like a coil, right? So you know how the inductor works, right? You know how the inductor works. So so this, if you have like an inductor here, when you know the Lenz rule, right? So if you can't remember, it's like the governing principle of the inductor is like the Lenz rule. So you have a positive terminal. So it's like the opposite. I mean, same mechanism like the capacitor, right? So when you like have a capacitor, you supply current, charge is stored in the capacitor, and once the supply is cut off, whatever the charge stored in the capacitor will go down in the form of current, right? And if you take the inductor, it's once again here we actually storing electrons as in a electric field. Here we are using a magnetic field, right? So whenever there's a polarity created, there's going to be a resistance from here because of the magnetic field induced. It will store the energy inside the inductor in the form of magnet in a form of like in a magnetic field sort of way. Whenever the power is removed, it will reverse its polarity in this direction and start supplying the stored current, right? And this is actually given by the voltage VL is given by L. This is the inductance EI over dt, right? So I think these you all are familiar with. So simply it's like the magnetic setup, right? So we are actually not concerned about this for the modeling because this is the permanent magnet in our case. So what this resistance is actually it's not actually a resistance, right? So it's simply an impedance, right? So if you take any coil, there's like a so what you call by impedance is the reactance plus resistance, right? So these are first year, second year of the timeline, like recapping. So this is actually what you're trying to model in this way. So our concern is about the rotor, right? So we'll see how we can model the rotor. Okay, so we'll see how we can model this. Okay, so just so this is like the armature circuit, right? Armature circuit. So I will model it. So and these equations I will show how it's obtained. Okay, because sometimes as soon as you see this, you might be wondering how these are obtained. So I will just work this through, and you will tell me how whether you are get it or not. Okay, so we'll go to the part. So we'll first do so basically DC motor has two parts, right? DC motor has the electric part and we have it also has the mechanical part, right? So I think the tip of this pen is sort of worn off, it's not writable. Anyway, so this is how actually this we can like categorize this. So we'll first look into the electric element. Okay, we'll look into the electric element. So you all saw in the lab sheet how it's the armature current is modeled. So now just think about this practically, right? So what is the armature? It's a coil, right? We have a coil. We have the terminals, power supplied from the brushes. This is like we are looking at one instance and we have a coil sort of thing, right? So it's like the winding, I'll check how the winding is done. So it's simply there's like a coil sort of thing. So this is like, wrapped around some sort of like a, you call that actually the commutator, right? So it's winded around that. So it's like a basically coil, right? So how can you like model a coil? How can you like you model a electrical conductor? What are the parameters? So any electrical circuit can be modeled based on 3 parameters, right? So it's resistance, inductance, and capacitance, right? But do we have any sort of capacitance here in the DC motor? No, right? There's no capacitance there. We don't have any storing element. No, we don't have any charge accumulating element in the DC motor, right? We don't have any filters. We don't have any sort of electric fields involved, right? We just have a coil, right? So whenever there's a coil, obviously there's an inductance. And when there's a conductor, so we have a resistance, right? So what we'll do is we'll model this, okay? We'll model the elements. So we have the terminals, given power. So we'll look at that at last, right? So we look at the powering up at last. So we have 2 terminals. We have the resistance of the armature, right? We call this the armature. So we have the resistance, we will denote it by RA. And we have the inductance. Let's move this out. I have the inductance of the armature. So please pay attention. I'll be asking questions, okay? So because you should know this, right? These are already covered stuff that we'll be doing. So you have the armature resistance and the armature inductance, and then there will be. So you all know, like simply you can, categorize that as the inductors effect. But always when you take a motor, there's something called a back EMF, right? Or the back electromotive force. Some sort of like electromotive force opposing the polarity created by here, right? So we'll assume we'll just keep that also, take that also into account, and we'll keep the motor here. So because not the motor actually, like it's like just simply like a parameter, okay? So so we have it like this. So we'll assume this is equal to VB, and this will assume the voltage, supply voltage is equal to VM, okay? And I'm using the terms used in here. So now we'll assume the polarity here is positive and negative, then the back EMF should be the opposite. It should be opposing that, right? So it should be positive and negative here. So what can we do? Now we can, so these are all the elements, right? This is armature resistance, armature inductance, the inductor, right? And the back EMF and the supply voltage. Now we'll use, we'll apply KVL to this circuit. We'll apply KVL to this circuit. So what does KVL say? The voltage, if you consider a loop, the addition, the summation of all the voltages of this particular circuit should be equal to 0, right? So we'll take, so I'm not sure how you guys are doing this, but I'll just go with in the method that I'm following. So basically we'll take the supply here. So this is actually it's a rise, right? The voltage rise. So we'll keep this as positive, VM, positive. And I will mark the, so you all have done power electronics, right? So you all know how to check the devices, right? So if there's a current, the positive current entering side is positive and this negative, right? So we'll mark the polarities like this of these devices, and we'll assume this is VRA. We'll assume the voltage at this point is VLA, and the current going here side. Okay. So there's a drop here, VRA. And then there's another drop here of VLA. And there's another drop here, VB. Okay, clear? So this is equal to 0. No issues there, right? So we have this equation. So we know we can rewrite this as VRA is equal to IRA, right? So I'll is IA, right? So this we can write this as VM minus IARA. What about VLA? So I said earlier, the voltage of an inductor is given by the inductance times the rate of change of current to the inductor, right? So we can write this as LA d IR dt minus VB. Now to this equation, we can apply a Laplace transform. Okay. So if we apply Laplace transform to this, what we'll be getting? So we'll be getting this, right? Something like this, right? We'll be getting EVM, S and all. So I will just, for the time being, for simplicity, I will just opt out this S domain, right? Now I write the equation. So we'll be just getting the exact same equation because these are all constant. And because these are just normal terms, and we'll be only getting this this part, which is actually varying time. The time variance part we will get as so we'll take capital IA times S minus V. So now we will try to now what we are looking at here is what's important, right? So we'll try to so obtain, in our case, we are actually looking at the current, right? We are looking at IA, the current. So we can isolate the current. So I mean, I think I have marked simply. I have to be consistent with my notation, right? So so I will get VM and VB out here. So I mean VM and VB, I can write it as this, and I can write this part in the other side, right? So I can write IA and RA here. So I will take IA out and write this directly. IA out of this, and I will write. So there's going to be RA plus LA. So if I want to get IA, I can write IA equals VM minus VB divided by RA. There's an S here, okay. LA is right. RA plus LA. So this is one of our equations that we want. Any questions of how we obtain this? Any questions? Any issues up to this point on how we obtain this equation? I don't think so, right? I think it's pretty simple how we obtain this. Okay, so we have one equation now of a model. We have a model for our current, right? Now we also know from our like theory that the torque torque of the motor, if we assume it's Tm, right? It's proportional, right, to the current. Okay, so Tm, that you're proportional to the current, armature current, right? The current that we obtained earlier. So now we can assume the proportionality constant is, say, Kt, and we can get Ia, right? So if we plot this, it's like in the form of y equals mx, right? So it's we have Tm is the Tm side, and we have Ia, and the gradient of Kt is going to be here, right? So this is going to be the form. This is going to be Kt. But we know in reality there's always going to be a loss of friction, right? There's going to be loss caused by the friction. So that we can actually write in this form, right? Tm equals Kt Ia. So out of this particular part, there's going to be a loss caused by the friction. We can denote it by Tf. Okay, so this is in the form of what? Once again, y equals mx minus c, right? So it's actually plus c, but the intersect, the intersect, I mean, where the y-axis is going to be intersect is going to be in the minus c axis, right? It will be in this form. The minus Tf, the gradient is still going to be Kt. Okay, everything clear? Clear, right? So we can assume this to be Tm and here it's going to be Ia, right? Okay, so this is one equation that we can plot. So we'll keep both these equations. This is going to be the ideal equation. It's going to be the practical equation, right? This pen is sort of okay. So we have this equation now. Any question how we got that? Okay, so we have that, and we can also get the equation for the back EMF. You also can get the equation for the back EMF. The back EMF, you know, is directly this will write back EMF, right? So back EMF, you know that it's like directly proportional to the shaft speed, right? We take the shaft speed as omega m. So then we can once again write this with the proportionality constant of Kb and omega m. So this we can call as the back EMF constant, right? Kb is equal to back EMF constant, right? So we got this, right? So we got this. So what we can do is we can so we can actually plot this. So if you plot this once again, you will get something like this. VB omega B BKB, right? Okay, so we have our back EMF equation given by this. So we have our electrical equations together, right? So if I write them all, in one slide, so I think the most complicated thing is getting the, now I think, so I feel like the biggest problem most of the students have is how to get the model, right? You all can, if you are given a block diagram, you all can solve it. If you are like given the transfer function, you can solve it. But the problem most people have is how to obtain the model, right? So that's what we are actually trying to discuss here. Okay. So now, up to this point, is everything clear? Hands up, people who are clear, having any issues. Okay, raise the hand, people who don't have any issues. So I know that who has everything clear up to this point. There's one student. Okay, so there's 6, 7. Okay, so there's a reasonable amount of students who don't have any issues. So 11. Okay, so up to this point, you all don't have any issues, right? The remaining people, are you all okay? Mafas, Pereira, and all, you guys are okay? Any issues? Mafas, any issues? Any point that you're not clear? Everything? You got it?
Yes, sir, no problem.
Okay, so you have any questions? Mudalige, you have any issues? Jayakram? Now, don't like raise your hand because I'm asking questions. If you honestly have any issues, just let me know. Okay. So what I did was simply this, right? I got the armature. So this is like the DC motor model. So we have the armature, we have the polarity, the magnetic field. So I just, yeah, you can draw the hands, right? I do this armature circuit, right? And I apply Kirchhoff's voltage law, and I got this relationship, right? So I hope everyone's clear with the KVL part, okay? And then after I got the, I applied KVL and I got a response to the this armature current, okay? After that, what I did was I used basic theories of motors, where we know that torque is proportional to the armature current, and the back EMF is proportional to the motor shaft speed, and we got derived this constants, and we got this relationship, right? So for the for the torque, there's going to be a resistance from the there's going to be a friction sort of thing. We reduced that, and we plotted it, right? The plots are not important. I just want to like show you how the results are for these, right? So these are linear plots. So I will actually write everything in one slide, the equation that we got up to this point, right? So we got the IA current is equal to VM minus VB, right? VM minus VB divided by RA plus LAS. This is one. Then I got an equation for the back EMF VB is equal to KB omega M. And then I got another equation for the torque equal to the constant, the proportionality constant of the torque, or its torque constant, times the armature current. This is the ideal one, but in practicality, we actually get friction where we get KT IA minus this friction of TF, right? Okay, so these are the equations that we got. So we can substitute this VB in this and we can obtain another expression for IA after substituting this on this. Substituting, right? So we can obtain an expression for this as Vm minus KB omega M over RA plus LA. Okay. These are our models, right? These are our equations. So now the question is, now we can obtain this, right? There's no question about this. Now, how can we obtain a model from this? How can we obtain a model from this? So we'll go step by step. Okay, we'll first try to model our equation. So what do you think is the best option to model? So I think we can model this, right? We'll first try to model this equation. So I will call this equation number 1. So we'll model equation number 1. So how can we model this equation? So we know we have to get this output, right? We have to get this output. But how can we get this output? So we'll consider one point. We'll get Vm. Okay, we'll get Vm. So we got Vm over here. We'll give Vm. So Vm has to be subtracted by this value, right? Vm has to be subtracted by this value. So we'll add a summation point here, right? And this is going to be subtracted. How is it going to be subtracted by? It's going to be subtracted by VB actually. This is what we actually wrote here. So VB, we have to get VB. So this is like a comment, okay? This is not anything. So how can we get VB? So we have to give omega m input. We have to give omega m input, but it has to be multiplied by KB. We multiply by KB. We'll add the KB sign here again of KB. The omega m. Okay. So omega m gets multiplied by VB and KB, and we get KB omega m. This one, right? Which is equal to VB, right? This VB, I think you might get confused if I had. So this will actually give KB at this particular point. KB. I will write this comment sort of thing in a different color, right? We will get KB. This pen is equal to VP. Okay. Okay. So this is like a comment. Okay. This don't get confused here. So move it a bit down. If not. Okay, so this is this point. Now this output, we get this output from here. Now this, whatever we get from here, we have to get in this form, right? So now we have got up to this point. Vm minus KB omega m is done. Now we just have to divide this by this. So what can we do? We can just multiply this by again. Of 1 over RA plus LA. Yes. So we have up to this point, and if we get the output here, we will get IA, right? So our first equation is modeled, right? Our first one is modeled. This equation is modeled. Now we'll see how we can modify this, right? How we can modify this. So we want to get the, say, torque, right? So we want to get the, we want to get this one. We want to get torque. It's 2, okay? So what can we do? So torque is simply IA multiplied by KT, right? So how can we get that? We just have to multiply this, right? We just have to multiply this with another block of KT. And then we'll get TM. Right? We get TM here. So we have done this. We have modeled this. Now we have to now back EMF, of course, we don't have to model because this was included in this, right? So these two equations have already been modeled. So this particular back EMF has been included here. So we are actually considering back EMF at this point, right? This is back EMF. This particular point is the back EMF, right? So we are taking into account back EMF. So this is also done. This is actually the remodeled version. So these two are combined together to form this, right? So we just have this. So this is the ideal motor. This is for the ideal motor, right? This is for the ideal motor. But in the practical scenario, there's going to be a friction on TM, right? There's going to be a friction here. So how can we add the friction? So before TM here, what we can do is we can, after KT is obtained here, we can at the summation point, I use the same color. We can at the summation point, and we can add this to a negative TF value. And you get everything. So this, out of here, you get the ideal TF, ideal TM. So ideal TM will be deducted by this TF, and you will get the actual torque. So this is our electrical model. This is our circuit, armature, DC motor electrical model. Are we done yet? No, we have got the electrical model, but this is not all. Now we have to consider our mechanical model. Okay. Now we have to consider our mechanical model. So, so I will quickly do that also. So if we consider the mechanical model now, so you know from Newton's second law, right? You know from Newton's second law, if there's a torque like that, so the sum of all applied torque, right? 1 to say n is equal to the, the moment of inertia, like of the entire body, right? So the moment of inertia of the entire body times angular acceleration, alpha. Okay, so this is like the model, right? So this is like the equivalent model of the F equals ma in an angular space. So from this we can obtain for J, if you take a DC motor in this case, so we have to find the moment of inertia. This can actually obtain Jg, can be obtained by so we can obtain the mass moment inertia of the armature motor armature, that's the one rotating. And if there's any load, that, right? If there's any load attached to the motor, that. So, so now from this, what we can obtain is, so the net torque generated by the motor, right? Net torque generated by the motor, we can obtain is equal to Tm is the torque. And if we assume there's some friction, right? So simply if we assume some friction here, is the friction value. If we are considering real cases instead of ideal, this will be equal to this, right? Jg alpha. So this is the force differ. I mean, this simply, like if you look at this in linear scale, it's like the force minus the you know, the, what do you call this, the resistive forces times, it's like ma, right? This a is like angular acceleration, m is the moment of inertia in angular space. So we can substitute this in here, and we can obtain Tm minus Fm omega m equals Jm plus Jl times alpha, right? So alpha, we'll write this as alpha m. So alpha m we know is equal to your omega m over dt, right? Because we don't want to add another variable inside, okay? So we'll write this in terms of velocity. So we can like remove this, you know, alpha, right? So we'll write this as d omega m over dt. Now for this, we'll apply Laplace transform. Now, so because we don't want to, why do we apply Laplace transform? You might be wondering why this one was like working on with the normal equation. Suddenly, in the earlier case also, whenever there's an inductor, whenever there's a like velocity, I go and apply Laplace. The reason is because we don't want to work with this differentiation marks, right? So whenever there's a differential term in the equation, you have to use differential equations to solve this. And we actually don't want to make things complicated. It's better if we can have it in the algebraic form, right? So we use Laplace, convert it into the algebraic form, and then use it. So use Laplace, we'll get the same thing. There's not going to be any difference here because we just have only one differential pair. And we'll get this. So this, after differentiating, we'll get, after Laplace transform, we'll get omega m. Yes, right? So I'll simplify this here. So if I isolate Tm over here, right? If I isolate Tm over here, that's the torque. I obtain, so I can move this over here, right? I can move this over here. So then I can write Fm omega m plus Jm plus Jl times omega m s, right? So I can take omega m out of here. I will get Fm plus Jm plus Jl times s. So this is equal to n. So if I can obtain this, so we know that the output is this. So if we like obtain this RPM over torque ratio, right? RPM over torque ratio here, we'll simply get omega m over Tm is equal to 1 over Jm plus JL times S plus Fm. So this is our mechanical model, simplified mechanical model for the DC motor, right? Pretty simple, right? So it's not very complicated, just some solving. And if you like look at this in a mathematical way, I mean in a block diagram way, we have Tm here. So you can like write this here. You can write omega m equals whatever you have here, whatever you have here, times Tm, right? How do we write this in a block diagram format? We have a Tm input. We send it through this model, 1 over Jm plus JL times S plus Fm, and you will get omega m, right? The multiplication of these two will give you, this is the model. This is the mechanical model. So now we have the electrical model and we have the mechanical model. So if I go back to the electrical model, we have this. So what was the mechanical model? It was Tm times this, Tm times, so I will try to avoid confusion here. That's right. Tm, so this is better if I use another color here, right? I write this in red. Mechanical model. So it's going to be Tm equals, also in this case, Q's into 1 over Jm plus JL times S plus Fm. We'll have omega. So what do we have to do to modify this? We have to combine DC model, what do we have to do? So we are getting a Tm here. We just have to add this Tm, write this here. We have a Tm here. We just have to add this Tm to the mechanical component. So I will write the mechanical part here, 1 over Jm plus JL times S plus M. And you will get omega. So this is our overall DC model. Clear? Any issues how we obtain this? Any problems up to this point? Anything unclear? Okay, so tell me, people who are clear about this, clear with up to this point? Okay, okay, so no one's clear. Are you all clear up to this point?
Yes.
Okay, right. So you see that how we got this, right? So I think you all understand, like you all should get the idea that everything is falling under place now, right? So you all have this, you all get a circuit like this, a physical model, like something like this. So something like this. So you simply you get the circuit diagram. Okay, simply this is like a coil, right? It's something like this, a practical coil. You model this, you apply Kirchhoff's voltage law, obtain this equation. Then you obtain other models like physics. Basically, in physics, you have proven this, right? For electromagnetism, you have obtained that torque is proportional to input current, and the back EM is proportional to the RPM of the shaft. So you can obtain these equations, and you can use these equations to like develop this equation. So you have like 1, 2 equations here. So you can use them to like derive a block diagram for the electrical system. And for the electrical mechanical system also, you got these equations from basically physics, Newton's laws, and rotations in angular mechanics, right? And you can substitute all these, solve them, simplify them, and obtain a relationship. So you have an equation for the mechanical model. And you combine both of them together, you find a common spot. So there's a TM here, there's a TM here. You try to integrate them, and you get the compound DC motor model. Okay. So this is basically it. I think this, so simply you just have to go to MATLAB, plot this, make the block diagram in this form, give inputs, and see whatever outputs you can obtain. You can obtain outputs for omega m, right? You can vary these inputs. So system parameters are obviously the same, right? So you can see how when you like change the terminal, velocity over here, sorry, terminal voltage over here, how the omega is going to change, how the torque is going to change over here, right? So you can simply check all these, right? And you can simply this is omega m. So this omega m, if you want to like make this closed loop, so this omega m is going to be a joint here, right? Okay. So so this is basically it, right? This is the simple model. After that, if you want to like set a, say omega m is going to be, so you can see now for control systems, you have simply learned about block diagram simplification, right? This is the reason, right? So you might be wondering, you have blocks, you have block diagram, algebra, and all these things. Why? This is the reason. Now you have a big complicated block diagram. You can simplify them, right? You can multiply these two together. You can move this sum around and do some operations. You can move this up, move the sum here. I don't know. So it's up to you. So you can simplify. You can obtain a simple transfer function in the form like this. You can obtain simple transfer function after simplifying this, where you have, say, something like this. So you have the input, you have the output, and you have a plant over here, like a plant model over here, and then sometimes feedback, right? So we can take this as GS, this is HS, and simply we'll get GSO 1 plus GSHS. That's going to be the characteristic equation, right? Or the system model. From the, that's going to be the transfer function, right? So this transfer function, you go and plot in MATLAB, and then you put a PID controller, and then you control it, right? So it's not very complicated, right? If you like understand the fundamentals here that we are talking about, you should be getting the entire point of this. Yeah. So okay, so any questions? Any questions? So I will quickly show you so simply in this case, you have to model this plant. I think that's a lab task. Yeah, you have to like derive these. So there are a few tasks, right? So so these things are we derived here. Okay, so PID, this is like the PID controller. Okay, so so you have to like model this. So this is like the last. This will most probably be your last Simulink based lab, or simply your MATLAB, unless you all do robotics in the 4th year. So so you can use all the knowledge, and this is actually the parameters. So you can use parameters as your inputs for your system, and these are the PID controller values. So you plot the system with these values. Okay, so you plot them with these values, and you can obtain. But I think, I mean, by any chance, if any students' names are not there in the list, let me know. Okay. If any students' names are not there in the list, let me know. I will give someone's values, and you can like solve, right? So so for those of you all whose names are not there in the list, I will add some more parameters in the bottom, so you can use those values and do the model. Okay. So I will add some more values in the bottom, and you can use those values and do the modeling. So yeah. So this is about that, and I just want to talk about the auto-tune parameter of the auto-tune tool of the PID controller. So I'll quickly go and finish that. So let's start to open MATLAB. So if you plot this, it's actually going to be somewhat, what you get is going to be somewhat like, I think where you have to model this is going, this is an example of an so without simply unsimplified model. Okay. So like an unsimplified model, you have to derive the variables in MATLAB script. So stars 2, I will run this. See here. So if you go here, I think you can run this and see the position variation, right? This is like just the model, right? So you can see the position variation with time. So now I will just talk about one important aspect, right? One thing would be needed. So imagine you have simplified this up to very small, I mean, just a normal transfer function. Okay, you have simplified this up to very small transfer function. I will say, so we'll we'll assume that the transfer function has these values: 0.001, and the denominator we'll say is equal to 0.005. After you substitute the values, you get something like this, right? So basically, just assume that. And this is like a third order system. Okay, we'll assume this is a third order system. We'll say this is 0.1. There's no constant term. Okay. So that's our transfer function. This is our transfer function. Okay. After simplifying, let's say we get this. Okay. So we'll give this step input, 1. And then we can actually say we get a scope here. So we can have a forward feed forward system, and we can assume how this actually works, function, right? So it's somewhat similar to what we are getting the feed forward system, okay? The position. So now we'll make this a feedback loop. So we'll get a sum over here. So we get this this here feedback. Okay, so now so this is a feedback loop. So we had to to make this to control this, we had a PID control. Okay, the PID controller, so we can get a PID block here. You can simply go and model this like this, right? There's no I mean limitation there. You can, if you're familiar with this way, you can simply go and model the KP, KI, KD, I mean gains here, and model it like this. We have a gain value, integrator, KD, derivative. You can use this, no worries, right? But I'm just talking about a simpler way to do this, right? Because in the industry also, I think if you're ever given to like model a PID, you can simply use this, okay? If you know the plant model, you can use this. Okay, so we'll get the step input also here. So we will say this is the scope to have 2 ports, right? So this signal out here. Yeah, this, right? So now I will run this. So now I'll run this. Now this without the PID controller, what we get is something like this, right? This is the input, step input, and yeah. So it's going to be 0. As soon as we get the step input, this is going to have a increase, right? So we change the system to second order. Say I make this this let's make this second order and see the second order response, how it is. Yes, somewhat. So I think it's like we'll make it a second third so that we can see the PID variation, right? Right. So now even in the PID controller, it's like this. So we go here, we can give certain values to the PID controller like this, right? So we can say we can give values such as say 1, 1, 0. So we'll give the 1, 1. So this is like a PI controller. So we'll see the response here, right? So we can like tune this system. So we can say frequency response based or transfer function. So we'll go with the transfer function based tuning. We simply click tune. If this is not linear, so if this is not linear, it will actually linearize the plant. Okay. So after that, you will get your response from the PID like this. Okay. So this is the, I mean, the block response is the tune response. Okay. So we can actually vary this. like this, right? So we can actually vary the response like this. So we'll say our settling time, we can response time, we can make it fast, right? So the response time is very fast, but there's going to be some sort of like a oscillation. So we can actually make the transient aggressive. It's going to be like a lot of oscillations, or we can actually make the transient smooth, right? Transient smooth, and we can make this thing slower and make it a very, so yeah, something like this, right? So we can actually, now this is, I think, sort of like an ideal response, right? So we can set the response like this. We can, sort of see, okay, so we'll just say this is okay, right? We are settling soon, right? And we just have to update the block like this. It will update, and it will calculate the optimum PID parameters, right? So it will say the P is 512.3, I gain is 177.7, D is 281.6. So if you go here, it automatically evaluates these. And here, this is the control they're using, right? And there's an N value here, which is for the filter coefficient. That's also calculated, apart from the PID. So now you can actually get that in the PID part, right? So you can see the output now, right? So this is one method that you can tune a system, okay? This is a much more easier way of tuning a PID controller. And you can use this method. It's a very robust way of controlling PID, right? So you can use this method for your projects and your task. So it says you can use any way, right? So you can say they say you can use the same PID. Sorry, does it say say a tuning part? Yeah, I think you have to use it to do a tuning part. You have to first use whatever the values given there, and then you can do it, right? So this is it for the lab. So any questions? Any problems, issues? And for the submission, I will give you all 2 weeks. 2 weeks is enough, right? Is 2 weeks enough? Or I can even, since you have the mid exams next week, I can even give you all 3 weeks if you want. It's not a huge, it's not sort of like a bulk lab, yes, but okay, I will give you all 3 weeks. Okay, so it's today's 12th. So your submission will be on the 2nd of September. Right, 2nd of September. I think that is good, right? You all can submit by then. Okay. Please submit PDFs, right? Just the report. If I feel that you all have done anything, suspicious, then I will actually ask for the codes. But from the PDF, of course, we can see, because we can see the responses. We can, anyway, you have these values, right? You have to use these values. You have individual values, right? So you have to use these values to do the modeling. Okay. So that's, I think that is fine. So I will stop the recording at this point. And I have some discussions to make. Some notices before that.